This is part 2 of 3 for section 1 of chapter 13. Now that we know more about dissociation, we can review precipitation reactions from last semester. Remember from last semester that while no ionic compound is completely insoluble, those of very low solubility can be considered insoluble. This is where we get our solubility rules. Your solubility rules you can find on page 437 of your textbook. You should also have a list like this from your last semester chapter 8 notes or from the midterm exam review. I will give you another copy of this in class. But a little reminder, the way we use this chart is we look at the soluble compounds and the insoluble compounds. And so any compound containing NO3- is soluble because there are no exceptions. Same with the acetate ion here. No exceptions, it's soluble. Chlorine and bromine and iodine are mostly soluble. The exceptions are if they're combined with silver, mercury, or lead 2. And finally on the top list, sulfate ions. Compounds with sulfate ion are soluble unless they're combined with strontium, barium, mercury, or lead 2. In the lower part of the diagram, we have the insoluble compounds. So these are ions that are typically form insoluble compounds. So sulfur, or the sulfide ion, will typically be insoluble unless it's with ammonia, the alkali metal cations, that's group 1. So we put group 1, and calcium, strontium, and barium. Carbonate ion, insoluble unless it's with ammonia or group 1 metals, the alkali metal cations. Phosphate, insoluble unless it's with ammonia or the cations in group 1, the alkali metal cations. And hydroxide, again, unless it's with the alkali metal ions or calcium, strontium, or barium. We'll go over this chart more in class and do some examples working with that. But for now, let's go back to our precipitation reactions. The reason we're looking at the solubility rules again is that the dissociation equations that we wrote before, they cannot be written for insoluble compounds. So we need to figure out whether something's insoluble or not before we try to work out the dissociation equations. And what we're working our way to being able to do is we're trying to be able to write net ionic equations, which is what the next video will be about. So we're looking at precipitation reactions. We want to know if mixing two solutions results in a combination of ions that forms an insoluble compound. If that happens, then we know a double displacement reaction will occur. And precipitation will occur. We will form a precipitate. We've talked about precipitation reactions before and double displacement reactions, but do we know what really causes precipitation? If you're not sure, I'm going to discuss it right now. Precipitation occurs when the attraction between the ions, I'll write that down in a second, when the attraction between the ions is greater than the attraction between the ions in the surrounding water molecules that the compound originally was dissolved in. So precipitation occurs when the attraction between the ions is greater than the attraction between the ions and the surrounding water molecules. Page 438 of your textbook shows this happening at the molecular level. It shows the before the reaction, what the two solutions look like, in which case the ions of the different compounds that you originally have are dispersed throughout the water. They're dissociated. The ions are all separated. And when you mix the two different solutions together, one type of ion from each solution are going to find the other ion from the other solution that when they combined, it'll form a precipitate. And when you see that in the molecular level, you'll see that grid of ions, alternating ions, form, and the water and the dissolved ions, the ions that are still dissolved, are pushed off to the side, and just the ions that attract each other more strongly are held strongly together, separate from the water. And you'll see that it's actually pulling itself out of solution in that way. To find out whether combining two solutions will result in a precipitation reaction as described above, we must first predict what the possible products are in a double displacement reaction, and then we must see if any of the products are insoluble. So this is just like what we did in Chapter